assume you're surrounded by a piece of metal. In your simulation, you can put field monitors, and in the assignment I'm going to ask you to do. Let me just go ahead and pass that assignment out. This is due next Friday. I will collect this. It's a CST assignment. It's not doing this one, but it's doing something similar. E-field monitor, an H-field monitor, and surface current monitor. And to do that, that's a tab you click. You click this thing, H-field, and surface current. So you click, if you're doing E-field, you do that. H-field, you do this puppy. And this is a far field, right here. Far field, that's one of the main things you want from the antenna. Okay? Let's look at the far field. This is the pattern. This is the pattern. Let's put the z-axis up like we're used to looking at it. That's better. So that's the you can see this is a dipole antenna, so it's going to radiate most strongly in the XY plane. It doesn't radiate very well at all in the X plane, the Z plane. Notice this directivity. It's given in dBi. We're talking about power, so what this directivity in dBi means is 10 times the log, not 20 times the log, of log base 10 of the directed gain over the directed gain of the isotropic antenna. What's the directivity of an isotropic antenna? It's just 1, right? So this is 10 times the log is 10 of D. So CST provides us directivity in terms of dBi. This is the thing this is the Vmax we've been talking about. Okay, so to compare your analytic result to the simulation, you'll need to pay attention to this formula. Very cool? Let's do the two-element array that we talked about right at the beginning. Let's kill the radiation in the X direction. Okay? So to do that, you right-click, far field properties, and you go to array. I want an antenna array. I want a two in the X, and I want to separate them by half a wavelength. I want to separate by 150 millimeters. The default unit is millimeter here. Yeah, Christian.
Sorry, would you like to get to that?
Give me.
Speakers.
I'm just right here, just looking at the smart field plot. Okay, right click. And then go to array property. I want 2 along the X, and I want to separate them by 150 millimeters. And I want to apply that puppy. And sure enough, we're knocking down the radiation in the X direction. See what I'm saying? It's acting like we expected, and it's going to be more stuff in the Y because they're working together in the Y direction. Let's take this ball and run with it. Let's say we want to do even more, and then we'll put 10 along there. And we'll say, okay, apply. And now we get quite a bit more directivity. Let's close this. See, that's pretty directed now. Let's say we don't like these lobes up here. We want to really focus on, we want to focus on the X-axis. So we could put these things, we could have an antenna array. We can line them along the X, but we can also line them along the Z-axis. Okay? To kill this Z stuff. So let's do that. Let's put them along the z-axis. Now when we put 4 here, that means 40 antennas on this array now, 10 by 4 array. So this is going to be, how many did I say? Oh, 150? Now let's get quite, see all the, so several of you asked me about lobes. See all the lobes that are starting to show up? The minor lobes because of the antennas, array stuff. And let's say we're a designer and we have no sympathy for the people actually having to make this thing. We'll do whatever the heck we want to. We have unlimited budget and stuff like that. So say, man, I want 10, I want 100, and I want to be in the Y, I want another 10. I want that 300 because I want to help the Y. That's 1,000 antennas in this array. It's a solid array now, okay? So just typing these little numbers, if you actually have to make this thing, my God, you know, how many $1 million do you have? But you can get a lot of directivity. Yeah.
What do you mean it's a solid array?
It's like a planar array would have line you'd have rows in the X stacked up in the Z, and then a solid array has layers back here. See what I'm saying? It's kind of a board cube. I don't know if you've watched Star Trek Next Generation. It's kind of like a board cube. Yeah.
Can you put
Suzanne and I have been watching the Star Trek Next Generation, so yeah, go ahead. It has nothing to do with the antennas. I'm sorry.
I'm sorry. Do they have to like adhere to rectangular coordinates?
No, you can do other things, I'm sure, and if you have a mind to, and this, you notice I left you wiggle room in this assignment. You can do whatever you want to. You can align them. In fact, you can use the dipole antenna like we've studied, but if you want to use some other antenna, feel free to go ahead and do it and simulate it. You can use any kind of antenna. You have freedom to do as wild a thing as you want to here. And you can align them in some kind of cylindrical fashion or whatever. Spherical, take the ball and run with it. Yeah.
So this, when you do this, it's all the antennas they're still oriented the same way, they've just been translated.
Yeah. And so that's why this is so quick, because the heavy duty work has been to do this analysis of the antenna pattern. But the antenna array is just a bunch of geometry. You can do that like that, right? I mean, a computer can anyway.
In the very beginning, you got rid of 2 different boundaries. What were those 2 boundaries again?
Let me go back to this. Model. The boundaries, open ad space. Is that what you mean? Yeah. I mean, look at the boundaries. Don't have electric boundary conditions, which means the tangential component of the electric field is 0, which means you're basically assuming it's surrounded by a node. Because you're not going to get a very good far field doing that. And don't do this magnetic thing either. It's kind of same thing holds. Open ad space would be just fine. This unit cell is for a grid, for a periodic grid. That's what the unit cell is for, like for I don't know, frequency selected surfaces and stuff, things like that.
What is the difference between open and open head space?
Open ad space, let's see. Open continues the boundary. It just extends it, and there's no open. What open ad space does is you have a computational thing and you're surrounded by air outside.
Okay.
And that's what open ad space is what I use. You want to go through and build one? Yes. Okay, so let's go here. Let's close.